Okay, good morning to all of you. Today we are at lecture number 18 regarding the topic join operation and some basics extension of the relational algebra. So before starting into the session, first kindly give me a response from any of you that am I audible and visible properly? Am I audible and visible properly? I want some response from your side so that I can start the session in a fruitful manner. So, am I audible and visible properly? I am still waiting for the response from your side, and just after that, I am entering into the deep of the section. Okay, Moinak. Okay, I got your response. Thank you, Moinak. Okay. So in last session we already discussed about the Cartesian product. The matter is that how you can design two table join. Meaning is that in last session we already discussed that thing. Okay. Yes, visible. Thank you to all. So in last session we discussed about the Cartesian product. So in Cartesian product, the basic operator that we use, that is the cross. Okay, the cross product basically we use. So in Cartesian product, we take a look here that in both of the basic condition is that in both of the table, I must one column must have some similarities, meaning is that same number of same type of attribute should be there. The length of the attribute should be matched. If match such type of things, then we can go ahead with the Cartesian product. So in Cartesian product, the main important thing is that, for example, if you take a look here, the left side, apart from the salary, just before the salary, this is the part of the instructor table, and after the salary column, from the teacher's ID to course ID, section ID, semester year, that is the part of the teacher's column. Now if you take a look here, you may check that here in instructor ID, only one faculty, that is starting with the ID 10101 and name is Srinivasan, and department is computer science, and salary is 65,000. Very good. And teacher's ID, three courses, that is CS 101, CS 315 and CS 347, that is consist of the teacher's ID, that is 10101. So meaning is that here only one for the one instructor ID, that is starting with 101, that is connected with all the rows that's present in the teacher's table irrespective of the teacher's ID. Meaning is that maybe only one instructor ID, that is 10101, such type of tuple are present in your instructor, but here three tuple that is starting with 10101 that is present in your teacher's table. But when we are going to merge this relation at the merged or in a transformed relation, we can see that the particular tuple from the instructor ID is mapped with all the tuples irrespective of any of the conditions. So here we can say that it's a kind of a like OR operation. For example, if you are considering for the logical OR operation, then the value are simply OR. Okay. So here in cross product or in Cartesian product, no as such similarities is maintained. So for that reason, we are going into the join operation. So join operation is basically, we can say that it's an extension of the Cartesian product or extension of the cross operation. So all of you please note down, join operation can be considered as the extension of the Cartesian product or extension of the cross operation. Meaning is that here instructor table must join with the teachers. Here instructor table must join with the table teaches, but here some condition is there, some relational predicate is there that should be satisfied. Meaning is that if you take a look here, that select the tuple, if you select the tuple from the instructor Cartesian product teaches, but where the instructor ID must be mapped with the teacher's ID. Meaning is that we must take all the values, means this is the Cartesian product of the instructor and teachers. From this table we select only these values, where the tuple information of the instructor ID is matched with the tuple information of the teacher's ID. So from this whole table we consider only the first tuple, then we consider this tuple, then we consider, for example, this tuple, then we consider this tuple only, because in this selected tuple the instructor id is matched with the teacher's id. So join operation can be considered like that. It is an extension of the Cartesian product operation or the cross operation, where some of the attributes should be mapped with the attributes of the other table. So if you take a look here, this is the things. Here Srinivasan 10101, only single instructor id is present in instructor table, that is mapped with 3 of the tuple, because in teachers table 3 tuple have the same teacher's id, that's why it's repeated 3 times. But rest of the things are quite good. Cards have only one id, that is 45565. Okay, both belongs from the computer science, salary 75,000. But here in teachers table with the teacher's id 45565, 2 subjects are there. What is the meaning of that? This particular instructor Srinivasan, starting with the id 10101, is take total 3 subjects in the from the subject pool. One subject in fall semester, another subject in spring semester, and another subject is fall semester. Meaning is that for all this course id, the instructor id is mapped with the Srinivasan only. So that's why when the instructor id is mapped with the teacher's id, means the same instructor is taking all these courses, then we mapped like that. So these are the joining operation. Here it is considered as the extension of the Cartesian product, where some of the attributes should be matched. So next is the joining operation can be expressed in terms of a theta. So if you take a look here, if you write this statement that a joining operation is consist of a Cartesian product and a select operation. Okay, so here R join is depend on some relational predicate that is considered as the theta. So R join is depend on the rules theta is equal to select from the R Cartesian product S, where theta is the rule base. Meaning is that select all the tuples from R cross S where theta match or theta satisfied. Here the theta value is considered as instructor id equal to teacher's id, that is considered as the rule base for the select operation and for the joining operation, whatever you can say. So these 2 expression are considered as the identical expression. You may express like that: select from the instructor cross teachers, where it meets instructor id equal to teacher's id, or you may read like that: instructor may join with the teachers, where instructor id equal to teachers id. These are the basics of the joining operation. Next we will focus on the union operation. That is very similar like the join operation. R union S, the term is union sign is quite same, it's like the discrete mathematics. So R union S can be possible when R and S, both the table must have the same number of attributes. Means we can say that in shorter term, that is the same arity. Okay, means R and S must have the same number of attributes or same arity, and as well as the attribute domain must be compatible. Meaning is that, for example, in R table, the second column of R has the same type of value like the second column of S. Meaning is that in each of the attribute, same type of data should be there and the data length should be like the same. So if it is match the similar kind of a things, then we can go ahead with the R union S. Basically meaning is that, for example, if 2 same type of instance with you, if 2 same type of instance are with you from a sample database or from a single database, then you can proceed with the union operation. Here is the union operation that project the course id from select the semester fall and year is 2007. Meaning is that for the year 2007, only from the fall semester find the course IDs, and as well as find the course IDs from the year 2018 and the semester is spring. So meaning is that here same type of table can be union if it have the same number of attributes and the attribute must be domain compatible. So this is R union S. Now we If you take an example from the previous table, you can take that thing that from the previous table, from the semester fall 2007, the course ID is, for example, CS101, CS315 and CS319, and rest of the values are from year 2018, and the semester is spring, and these are the course IDs. Okay, I already say you that thing that you should take a snapshot from this table. Okay, you could take a snapshot from this merge table, that will be beneficial for further purposes. Okay, so these are the result using the union operation. Next we got into the R intersection S. In R intersect S, it is considered as the set intersection operation. Previous one is considered as the set union operation. Here it is considered as the set intersection operation. All the conditions are same, that just the sign is reversed. Means in R and S, in both the table, which values are considered as same, that value should be repeated here. Meaning is that in fall semester of 2017, the course ID is equal to the spring semester of 2018, that result should be derived. So CS101, such a course that should be taught in the fall semester of 2017 and as well as in spring semester of 2018, and both the table must have the same attributes, and the attributes should be compatible, means the same domain name as well as same domain length. Okay, now we focus on the set differences. Set differences is a quite new type of a term for you, but it's same like the R intersection S and R union S. Conditions are same. Both the table R and S must have the same attribute, and the attributes must be domain compatible. So here R set difference S or R difference S means is that whatever values are extra in R, that should be predicted. Whatever values are extra in R, that should be focused. So here the same example from the fall semester of 2017, these course IDs are extra comparative to the spring semester of the year 2018. So these are the basically the three operations that is very important: R union S, R intersect S, and R difference S. So next is the assignment operator. Assignment operator is not like actual the mathematical term is there, means it's just a show. Meaning is that if you just don't read this statement, just focus on this example here. Select the department name, select all the instructor where the department name is physics. Meaning is that whatever expression you are putting, from this expression in left side just put a arrow, and in left of this arrow put the rules or put some part of your expression. Got my point? Means whatever expression you are just going to execute, in left of this expression put a arrow sign, and in left of this arrow sign just put some part or meaningful part from your existing expression. Okay, so that is considered as the assignment operation. So here is the thing, it is convenient at times to write a relational algebra expression by assigning parts of it to temporally relational variable. Okay, so here find all the instructor in physics and music department. How you can find all the instructor in the physics and the music department? Here you find all the instructor from the physics department, and here you, using this assignment operation, you find the instructor from the music department, and after that you may union it. Okay, so with the assignment operation, a query can be written as a sequential program consisting of a series of assignment followed by an expression whose value is displayed as a result of the query. Meaning is that for a longer expression, the sum part is considered as the sequential query, and the sequential query is formed as a part of the main query, and after getting this result we just simply put this result in the main operation. So this is the task of the assignment operation. So next we are focused on the rename operation. Rename operation is very important here. For example, you already use that thing in your SQL, means the naming convention. For example, if you look like that select name from the table, select name from the table, for example employee. So this is a simple example. If you execute this query from the employee table, the name column would be visible. Now if you read like that, select name as EMP name, select name as EMP name from employee, Then from the employee all the name will be displayed, but in that case the column name should be changed as the employee name. Meaning is that whatever result or whatever expression you are going to display, if you want to rename it or if you want to change the naming convention, then you use this particular operator, that is the row operator. So here the meaning of this row means the rename operation of the expression is considered as the expression and x is considered as the naming convention or the rename value. Okay, so row x capital E means rename the expression capital E or rename the result of the expression E as x, and it sometime written as row x capital E means for the expression put the rename value as x, and in bracket of the x put all the attribute names. Sometime this notation can be used for the rename operation. This one is valid and this one is also valid. So moreover, here we already discussed all 6 basics operation of the relational algebra. Now we are looking into that some of the equivalent queries. For example, just take a look here. Exam questions will be come in this pattern. Okay, that example. For example, find the information about the courses taught by the instructor. Find the information about the courses taught by the instructor in the physics department with salary greater than 90,000. So meaning is that simple meaning is that find out the instructor name whose belongs from the department of physics and the salary is 90,000. Very good. So that's why we use the select operation. So now the basic question is arise that, sir, when we use the select operation and when we use the projection operation. So there is no as such limitation is there. In database there is no as such limitation is there. You must go ahead with the select operation or you must go ahead with the project operation. Because in database or in SQL structured query language there is no as such rule is there. Everything is depend on the user credibility. Whatever user think, you should process it in that manner. Okay. At latter part, when we will discuss about the cost of the query or cost of the tuple, then probably we will focus in some part that select operation will take much cost or project operation will take much cost. But here, when no as such rule is there, we have no barriers. So basically we have some assumption. This is my personal assumption. When you are focused on the whole attributes, or some part of the table in as it is format, means no drop in the attribute, just listen my point and if it is possible may note down. When you focus on all the attributes or some part of the table with all the attributes, then you should go with the select operation. And when you need a single or some of the column but not all the column from a table, that may be whole column or part of a single column or part of the sum column, then you may use the projection, project. Got my point? When you select all attributes, then you use select. When you take some of the attributes, then you select project. So here for this expression, we design the query like that. Select the department name physics and the salary is greater than 90,000 from the table instructor. That thing can be written using two select operation. If you break this AND operation in two part, for example, first we find all the instructor where the salary is 90,000, here it's not dot, it's comma, maybe it's a spelling mistake, it's comma. Here select the salary of all the instructor where the salary is greater than 90,000, and whatever you getting the result, after that you finding only this tuples where the department name is physics. So using one select operation and AND operation you can express that thing, and using two select operation you can add that thing. Okay, so that is up to you. It's consider both the queries are not saying that it's identical, but the meaning is equivalent. So that's why I put this example. So here are some more that sometime you may put like that. Select the department name physics from the instructor, join with the teachers where the instructor ID is matched with the teacher's ID. and as well as you may written like that, select the department name physics from the instructor and then join the value with the teachers table where the instructor ID is met with the teachers ID. That is up to you. Okay, so these are the equivalent query for that when the instructor from the physics department, all the instructor from the physics department is targeted. So these are the basics about the relational algebra. We completed the relational algebra part, means only the relational algebra part here. So some more operations are there that is not actually considered as the basic means the important aspects of the relational algebra. Basically 6 operations are in relational algebra. Apart from that, some more operations are there that help the common query processing and some extension. So till now that is the relational algebra. After the next part we will use some extension. Yes, I got one query. So here we will use natural join operation. Yes, we can use. Okay. So next we focus on the next part, that is the relational join operation and some extension about the relational operation. So just wait for a minute. I am just changing the slides. Okay. I am just changing the slides here. Okay, so now I am changed the slide, meaning is that we already know the basics operation. Now we can perform some of the queries. So here is an example. If you are considered, all of you first take a snapshot of this slide because it's very important. Take a snapshot of this slide because total 6 tables are there and each of the table have some of the attributes. Okay, first take a snapshot. So here total 6 tables are there and each of the table have some of the attributes. Okay, so just take a snapshot of that because depending on this structure we will further proceed our examples. Okay, so branch is there, customer is there, account is there, loan is there, depositor is there and borrower is there. If you ask about that loan, so if you ask about the account, so here two type of account is there, loan account is there and depositor account is there. Okay, and if you are asking about the customer, so customer may have borrower and depositor as well. Okay, so if you check the similarities here, if you are asking for the account, so account may have 2 3 here, account may have loan with the loan number and deposit with the account number. Okay, so total 6 tables are there. Now we are focused on the next. Find all the loan that is greater than $1200. So the operation is basics, simple. Select the amount that is greater than 1200 from the loan table only. From the loan table only, where the amount is greater than $1200, we just proceed. Very good. Now find the loan number for each loan of an amount greater than 1200. Now we are going into deeper, meaning is that from the loan table only select those loan whose value is greater than 1200, and from this tuples we are just focusing on a single attribute, that is the loan number only. Got my point? Okay. Now next, find the name of all the customer who have a loan, comma, an account or both from the bank. Meaning is that find the customer, those may have loan as well as may have a depositor account or the both. Meaning is that we are just simply union the values. Meaning is that either they have a loan, either they have a deposit, or they have both of these. Means the total participation here. That's why union. So we select the customer name from the borrower table as well as we project the customer name from the depositor table and simply union the values. Okay, simply union the values. Okay, so here union is possible. When union is possible, we know the term when the attributes have same type of compatibility. Obviously the borrower account have customer name and the depositor have the customer name, and the customer name have the same data type and the same data length. Okay, now next, find the name of all the customer who have a loan and a account. Meaning is that the customer name must fall in the borrower table and must fall in the deposit table. So that's why we need the intersection. So this type of queries is possible. Various types of queries are possible. For example, find the name of all the customer who have a loan at the Perich branch. So first our target is that from the borrower and the loan table we create the Cartesian product. From the borrower and the loan table we create the Cartesian product. Now we match the borrower loan number and the loan roll number, and from that we select the branch name Perich, means these tuples, and after that we are just showing the customer name only. So in different way we can use this type of queries. So these are the simple type of examples. You may find lots of examples in your books. You may practice these things more, because any type of expression can become in your examination. Okay, so next we have focus on some of the formal definition. Formal definition is a very important. Formal definition meaning is that the expression, a basic expression in a relational algebra consists of either one of the following. So a basic operation, so these are considered as the expression starting from the project balance ending with this part. These are considered as the basic expression. So a basic expression is in relational algebra is consist of either one of the following. Either it have a relation in the database, meaning is that some relation of the database. Here it's considered as the relation, that some relational algebra or relational operation is there. Expression is consist of the relation of the database. Either a constant relation, means a simple table. For example, customer have customer name, customer number, and customer city. That is only. Either it have a expression must have some kind of relation using the selection, projection, and some other operation, or it must have a simple constant relation. That is dependent. So now if we consider E1 and E2 both are the relational algebra expression, the following relational algebra expression can be performed. For example, E1 union E2, E1 difference E2, E1 Cartesian product E2. Here select the expression 1, depend on the predicate or the rules. Here project the value of expression E1, depend on the attribute name S, and here rename the expression 1 or the expression outcome or value by the value of X. So these are the formal definition of the expression. Now some additional operation are very important in relational algebra. For example, we already know the join, set difference, join, natural join, this kind of operation. Here we are focusing some of the basic additional operation that is not as considered as the core operation of the relational algebra, but that is considered as some added power in your relational algebra. So that is set intersection, natural join, and division, and the assignment. So in between that we already studied set intersection and assignment, and we already know some of the natural join concept, and now we are going to discuss about the division. So next is that here it is the set intersection. We already discussed that thing, set intersection. R intersect S means from both the table those particular column or those particular tuples value are matched. We focused on that, and rest of the conditions are same. We already know that thing. So here if you take a look here in this table AB, that is R table, that it is table. In this 2 table, alpha 2 is common only. Okay, that's why we depend on the alpha 2. Very good. Next is the natural join. That is a very important. So natural join we already discussed. Natural join and simple join operation are just same operation. That is R join S. So R and S must have some matching in their attributes. Okay, R and S must have some matching in their attributes. Just take some example. R have total 4 attributes A, B, C, D. S have total 3 attributes E, B, D. Very good. So here in R and S, B and D, both the column are matching. Just take a look at that. And the result schema name is A, B, C, D, E. And the result schema name is A, B, C, D, E. Very good. So, R join S means select, R join S means first select the tuple which have RB, means which have the same B value from R with the same B value from S, comma, as well as which have same D value from the R and same D value from the S. Got my point? Select those tuples only, those have same R value for B and same S value for B, as well as same R value for D and same S value for D. Means from the R Cartesian product S, we already discussed that thing, that joining is an extension of the Cartesian product. From the Cartesian product table, we find the values depend on some relational predicate. So depend on some relational predicate, we select the values from this particular Cartesian product and we project all the values like that. R of A, R of B, because R of B is common of S of B, R of C and R of D. R of D is common of S of D as well, and S of E. Meaning is that if you discard the left side part, that's have no impact. So if you add this left side part, that is okay. If you not add this left side part, that is not okay. So here is not important of that thing. Join and natural join operation are quite similar and is almost similar. If you take a look here in this example, it's a very important example. Just focus on that. R table have total 4 attributes A, B, C, D. Very good. S table have total 3 attributes B, D, E. R have some of the values, B, D, E have some of the values. Now we focus on the step by step. Now we focus on how many attributes are common in both of the table. So here in both of the table, BD is common and here BD is common. Now we go into deeper into the value. In BDE, in first tuple, we got 1A. Now we check that. In BD of S, 1A is there and again another 1A is there. Very good. Next we going deeper. We check here 2A is there. Here no 2A. Very good. 4B is there, no 4B is there. Here we again check 1A, A is there. So we take, here we check, again 1A is there and 1A is there. Very good. 2B is there, here we check, 2B is there. Now how we can map? First we take the 1A from that is the 1A. And for this 1A that is common here, okay, first we take this 1A. So here in this 1A, alpha, for the A attribute, alpha is there, we take the alpha. Very good. And for the matching 1A, here alpha is there in E. So the attributes is like that, alpha 1, alpha A. So the A value and the C value are come from this R table and the E value is come from this table, and the 1A is matching in BD column here and here also. Very good. Now next we going deeper, we checked the same BD value first 1A is matching with the second 1A of the S table. So for this matching we consider alpha and alpha in A and C as well, and in gamma and in E part we consider the gamma, because this 1A is matched with this 1A also. Means is that here only one 1A from the R table is matched with the 2 of the 1A from the S table. That's why this whole tuple is repeated 2 times with the different E values. Here only one E value is alpha and another E value is gamma. Very good. And next time for the second 1A from the R table, the same thing is repeated. For the second 1A from the R table, the same thing is repeated. So that's why it repeated, because for the same 1A we got the different E values, here the alpha and here the gamma here. And for the 2B, Here the same exact matching means only one tuple with 2b here and only one tuple of 2b here. That's why the exact match we just put it. So from this particular relationship, this is the natural join concept. So next we focus on the R division of S. R division of S is basically used when in some expressions of for all is used. When in an expression for all concept is used. Okay. So what is the meaning is that? Meaning is that just a simple example I am just giving you, not go for the mathematical operation right now. If R is consist of attributes a1, a2 dot dot am and comma b1, b2 dot dot bn. Okay. Meaning is that R may have total 10 attributes and S may have 5 attributes, that is b1 dot dot bn. So now R division S. Now R division S means you just display the result of R. You just display the result of R for the attributes a1, a2, a3 dot dot am. Okay, means the extra part from the R that is displayed. So here R divided by S equal to T, where the tuple T is belongs from the RS is belongs from the R minus S. Here just take a look here. R divided by S equal to first T. T is a tuple and the tuple is belongs from the relational table R and R minus S values. Okay, from the relational table R we fetch the R minus S, means the attributes with a1, a2 dot dot am. We select these tuples and for all the tuple U, and U is belongs from the relational table S irrespective of any condition, meaning is that T into U is subpart or is belongs from the global table, that is capital R. Okay, so these are the things. Means here first we select the tuple T from R minus S position and we merge and we end the table and we end the tuple with all the tuple of the S, and after that we finding the TU, means the exact matching from the R table only. After that we are finding the exact matching from the R table only. Just take an example here. Here AB, R table is consist of AB. Very good. AB have some of the values, and here B table have consist of only a single attributes, 1, 2 is the value. Now we finding the matching. Meaning is that here, for example, here in B 1 is there. So if in B 1 is there, find here in R table how many 1 is there. So here we find that 1 have alpha values, 1 have beta values, 1 have gamma values, 1 have delta values, and 1 have eta values. Okay, very good. So for B1 in S table, if we find in B values for the 1, here we find alpha is there. Here we find with the B1 the A values are alpha, beta, gamma, delta and eta. Very good. Now check for the 2. For the B value, the same B value 2, which one is the alpha value? We get alpha is there and beta is there. So for the 1 value we get alpha, beta, gamma, delta and eta. Total 5 values. Got my point? And for the 2 values we get the alpha and beta only. So that's why we saying at initial level for the B values, whatever different value set we are getting, and from this different value set we take only the common portion, that with the 1 we get alpha, beta, gamma, delta and eta, and with the 2 we are getting only the alpha and the beta. That's why we select the common part, that is considered as alpha and beta. So here the result is that we are focusing on the extra attributes, that is A, and from these extra attributes we are focusing only those values those are common from both the B values. So these are the concept about the R divided by S. So if you take another example here ABCD is there. So ABCD have some of the values, and here DE is there. So now you find here in DE, this DE have a exact match in DE column here in R table. So DE have A1 values, first A1. For this again gamma, means here we got some combination alpha A gamma, beta A gamma, gamma A gamma, means total 4 values we get. Very good. For beta equal to 1 we get alpha A gamma and gamma A gamma. Now if we take a look, for the A1 we get total 1, 2, 3, 4 values. For the beta 1 we get 1 and 2 and 3 values. Okay. For the A1 we get 4 values, for the beta B1 we get total 3 values. So now we finding what is the exact match. The exact match between A and B is in this two tuple, that for A1 that is alpha A gamma, and for the beta B1 alpha A gamma, and for the A1 that is gamma A gamma, and for the B1 that is gamma A gamma. So we just focus on these results. So that is the meaning of the division. Again I am repeating, at the time of division we discard the common attributes, we focus on the rest of the attributes of R, and from this rest of the attributes we are finding the values, that is the exact matching between the values from both the relationship from the common attributes. Okay, so these are the division operation. So next we are focus on the assignment operation. We already discussed that thing, that assignment operation in previous, no need to discuss anymore. So here is some type of examples are there. For example, that if you select that find all the customer who have an account from at least the downtown and the uptown branches, meaning is that here is the simple query that select the depositor join account. Select all customer means those who have an account and the deposit as well, and those who have a borrower as well. Okay, so here the depositor and account is first joined, and from here we select the downtown branch and project the customer name only, and intersect the values, that the depositor and the account joining groups, the city is uptown and the customer name, and we intersect the values because here and is there. If odd is there, then we put here union. So this type of example is exist. Okay, so next is the some generalized projection concept is there, that is depend on some mathematical aggregate function you already used in your SQL, that some aggregate function may be used, for example average value, minimum value. So here till the slide number 18 we completed. Okay, so from the next session we have focused on the slide number 19. Okay, so hopefully I am expecting that by tomorrow I will complete the relational algebra module, that is module number 3, and probably from the next week we will start on the module number 6, that is transaction, because module number 5 functional dependency have already completed by ma'am, and module number 4 that is SQL, you are going with SQL in practical session only. So till now that is up to you, and next session we are starting from the 19. Okay, slide number 19, that is of the extended relational algebra operation. Okay, so now I am sending you the quiz link. Just take a look here, that quiz link is valid till 11:20 only, not by 11:30 only, that is till 11:20 only. I am posting you the quiz link. Okay, I am just posting you the quiz link. So if you have any query, any question, anything, if you have any query, any question, anything, just get me informed. If you have any query, anything till now, whatever regarding whatever I have been completed today, if you have any query and any question, kindly inform me, please. Okay, I am posted the quiz link. Complete the quiz by 11:20 only. Okay, by 11:20 only complete the quiz. After that it will be just locked. If you have any question, kindly send me. So in next session probably we will focus on the rest part of the relational algebra, and our main target is that by the next day, means tomorrow, we should complete the relational algebra, means the module 3. Okay, so near about if you take here, near about 39 means 38 slides more to complete the relational algebra. Important and as well as very easy parts are pending. We will obviously complete that thing tomorrow. So if you have any question, kindly get me informed. Okay, so from the next session we will focus from the slide number 19.